In this video, we are going to discuss about IC723, which is a general purpose regulator. Let us discuss the features of IC723 first. Here, it requires a unregulated DC power supply voltage at the input, that is between 9.5 volt to 40 volt, and it will produces a adjustable regulated output voltage, that is between 2 to 37 volt. It has a maximum load current of 150 milliampere. It is represented by IL max is equal to 150 milliamps. A is missing here. With the help of additional transistor, the IL max goes up to 10 ampere. So it requires a positive or negative supply voltage for the operation. It will dissipate the power internally up to 800 milliwatts. So it is having a short circuit protection, and it will produces a very low temperature drift, and it has a high ripple rejection. So next let us discuss about the functional block diagram. So the functional block diagram of IC 723 is divided into 4 blocks. First one is a reference generator block. Next one is error amplifier. Next one is series pass transistor, and a circuitry to limit the current. So this is a pin diagram of IC 723. First pin is no connection. Second pin is current limit. Third pin is current sense. Fourth pin is inverting input. Fifth pin is non-inverting input. Sixth pin is V reference. Seventh pin is minus VCC. And eighth pin is no connection. Ninth pin is VZ. That is a voltage across the Zener diode. 10th one is V output. 11th one is VC. And 12th one is VCC, positive power supply. 13th pin is frequency compensation, and 14th pin is no connection. So this is called as a dual in package. Okay, that is in both side I have inputs. Both side I have pins. So first let us discuss a reference generating block. So here you can see it consists of the temperature compensator Zener diode, constant current source, and voltage reference amplifier together, which will form the reference generating block. So the Zener diode is used to generate a fixed reference voltage internally. The constant current source will make the Zener diode to operate at a fixed point, and it is applied to the non-inverting terminal of an amplifier. The unregulated input voltage plus or minus VCC is applied to the voltage reference amplifier as well as the error amplifier. Then only it will function. So you can see the functional block diagram of IC 723, and this side is nothing but a voltage reference amplifier. You can see the plus V and minus V is connected to the voltage reference amplifier and error amplifier. Okay, so the V reference is connected to the non-inverting input of the error amplifier. Okay, so next functional block is error amplifier. So error amplifier is a high gain differential amplifier with two inputs, inverting and non-inverting terminals. The non-inverting terminal is connected to the internally generated reference voltage. Then the inverting terminal is connected to the full regulated output voltage, plus V0. Okay. Third one is series pass transistor. So here Q1 is the internal series pass transistor, which is driven by the error amplifier. This transistor actually acts as a variable resistors, and it will regulate the output voltage. The collector output, that is the collector of the transistor Q1, is connected to the unregulated power supply. The maximum collector voltage of Q1 is limited to 36 volt. The maximum current which can be supplied by the Q1 is 150 milliampere. Next, circuitry to limit the current. The internal transistor Q2 is used for current sensing and limiting. Q2 is normally off transistor. It turns on whenever the ECC exceeds the predetermined limit. Low voltage, low current is capable of supplying load voltage, which is equal to or between 2 to 7 volts. So the V load is equal to 2 to 7 volt and I load is equal to 150 milliampere. So this is a IC 723 low voltage, low current typical circuit connection diagram. Okay, so you can see the R1 is connected between V reference and non-inverting input, and you can see R2 and C reference are in parallel. So if I want to find the value of the voltage across Ni, that is equal to V reference into R2 divided by R2 plus R1. Okay, and you can see I have produces regulated output, right? So R1 and R2 which will form the potential divider between the V reference and ground. So the voltage across R2 is connected to the non-inverting terminal of the regulator IC. So next the gain of the internal amplifier is large, that is the V non-inverting is equal to V in. Therefore the V naught is connected to the inverting terminal through R3 and RSC must be equal to V non-inverting. Okay, so the V naught is equal to V not inverting, that is equal to R2 divided by R1 plus R2 into V reference. So here the R1 and R2 can be in the range of 1 kilo ohm to 10 kilo ohm, and the value of R3 is given by R3 is equal to R1 parallel with R2. RSC is a current sensing resistor which is connected between the CS and CL. The voltage drop across the RSC is proportional to IN. This resistor supplies the output voltage in the range of 2 to 7 volts, but the load current can be higher than 150 milliampere. The current sourcing capacity is increased by including a transistor Q in the circuitry. The output voltage V naught is equal to R2 V reference divided by R1 plus R2. So this is a circuit connection diagram for the IC 723 low voltage and low current. So internal structure is this one. Okay. So here the pin number is changed because I have used a V plugin package top view. So in this one I have connected this R1, R2, C reference, C and R3 R3 and RSC resistors. Okay, RSC, R3, C1, C reference, R1 and R2. Okay, so here you can see this RSC is nothing but a current limiting resistor. So this IC 723 is used for protecting the short circuit current. Okay, so the question they may ask is draw and explain how the IC 723 voltage regulator could be modified to supply a voltage range from 2 volt to 7 volt. So we know that the V reference, so the V reference is nothing but 7.1 volt. Okay, so I can what is the voltage at this point? At this point I can write this is V non-inverting. Okay, so the V non-inverting voltage is nothing but So here V reference is in the 7 volt. Okay, so 7 volt into 7 volt into R2 divide by R2 plus R1. So if we choose the value of R2 and R1, you can get the value of V non-inverting, so which is nothing but your V naught. Okay, and we know that R3 is nothing but R1 in parallel with R2. Okay, so let us discuss how this RSC resistance is used as a current limiting resistors. Okay, so let me assume the voltage across this one is V sense. Okay, so and the V sense value is nothing but um, let me take that as 0.5 to 0.6 volt. So so the V sense is between the base and the emitter of the Q2 transistor, right? So I can write this V sense. V sense is nothing but VBE, right? That is nothing but 0.5 volt. So which will not turn on my transistor Q2, right? So suppose when there may be a chance of short circuit, means if short circuit happens, there will be more current will flow through this resistance, right? So that will happen only when the input voltage is maximum, right? And also see if maximum current will flow, the voltage drop across this RSC, right, will be more, right? So if if short circuit happen means, okay, means the V sense value must be greater than 0.5 volt, right? So it will be greater than 0.5. Okay, so if it is greater than 0.5, suppose if I assume the voltage is 0.7 volt, so which will make my Q2 to on, right? So it will make my Q2 to on. So if Q2 is on means whatever the current that will flow through, uh, so whatever the current here, right? So that will flow through this path, right? So this current is from this path, right? So instead of going to the base of the Q1 transistor, the entire current will flow through Q2 transistor. So which will make my Q1 transistor off. So if the Q1 transistor is off, the maximum voltage, so um, that will not reach the V load. So this will act as a short circuit protection, right? So if Q2 is on means Q1 goes to off state, so which will protect my short circuit at the load. Okay, so so here if you see the RSC value, RSC is nothing but V sense divided by IL. Okay, so the V sense value initially is 0.5. So the voltage across this one is V sense. So V sense divided by the current flowing through this one is IL. So the maximum current it will flow is 150 milliamps, and V sense value is 0.5. So thereby I can find the value of RSC. Okay. So the disadvantage of this method is it is current limiting. It is nothing but current limiting method, right? Constant current limiting is there is a large power dissipation in the series pass transistor Q1 when the load terminal is short circuited. Thus, the large power rating is required. So, in order to avoid this, we will go for the foldback current limiting circuit. Okay. So if we see the foldback current limiting cycle, now I have added two resistance. One is um, R5 and R4. Okay. So if I assume the voltage at this point is V1, so what is the voltage at CL? So the voltage at VCL is nothing but V1 into R4 divided by R4 plus R5, right? So what is if I want to make this Q2 to on, the VCL, right? VCL minus, this is nothing but V naught, right? VCL minus V naught must be equal to 0.7, right? So um so let me assume if this voltage is such that if it reaches value 0.7, okay, if it suppose it reaches 0.7 volt, okay, and it will make my Q2 to on, right? If Q2 is on means in a similar way, the current instead of flowing to this path, it will started to flow in this path, which will um, reduce my voltage at V1, right? If it reduce the voltage at V1, because there is no current flowing through this, uh, it will not turn on my Q1 transistor, and really my V0 voltage tend to reduce, right? So if V0 tend to reduce means still my current is uh, till my the Q2 is on only, right? So the Q2 is on since the VCL is greater than V0. Okay. Since the Q1 is off, the V0 start to reduce. Thereby, the VCL value is greater than V0. So which will make my Q2 transistor to on state only. Okay. So if you see the diagram, so this is how my IFL will look like. So instead of reaching the I knee value, okay, so it will reach only V0. Okay, this is about the load current. So instead of reaching the 150 milliamps, the greater value, okay, since the voltage value get reduced, the current get fold back. What is the value of V1? So I can write this V1 is equal to ILRC plus V0, where the current flowing through this one is I. Okay, so I can write I is equal to V1 divided by R5 plus R1 if the base current is very less, right? So the like getting the base current, I can write I is equal to V1 divided by R5 plus R4. So what is the value of VCL? VCL is equal to I into R4. So you substitute the value of this equation. This is my second equation. Okay, so this is my second equation. Third equation, so you will get V1 R4 divided by R5 plus R4. So instead of V1 you substitute this, instead of V1 you substitute the first equation value. So you will get VCL is equal to ILRC plus V0 into R4 divided by R4 plus R5. This R4 plus R4 divided by R4 plus R5 I am taking it as K. So I can write VCL is equal to K into ILRC plus V0. So we know that the VBE. So what is VBE? This is nothing but VBE, right? So this is VBE. So I can write VBE is equal to VCL minus V0, right? VCL minus V0. So if you substitute the VCL value and V0, I will get VB is equal to KIL RSC plus K minus 1 into V0. So from this one, I can take IL is equal to VBE minus K minus 1 V naught divided by K into RSC. So this VB divided by K RSC minus I will get K minus 1 into V naught divided by K into RSC. So this IL represent rated load current. Okay, load current is also called as knee current, that is equal to ISC. This term I am going to write it as ISC. ISC is equal to VB divided by, so VB is nothing but my V sense, right? V sense into K into RSC. Okay, plus K minus 1 minus K into V naught divided by K into RSC. So you can see the IL values, rated current values more than the ISC value, right? So whenever the output is shorted, this current get decreased, right? So the current start to decrease rather than increasing. So thus the series pass transistor Q1 is protected. So you can see the ratio of this rated current and ISC is depend on the value of K, and the K is nothing but 2 to 3 times the short circuit load current. So if you see the characteristics of the foldback, current foldback, so this is the characteristics. You can see the IL value is greater than the ISC value. So what will generally happen if so for the load get increased, the voltage falls backward, right? So the voltage falls backward and finally it becomes 0 at ISC. So and it is less than the rated load current. Hence this protection circuit is called as foldback protection circuit.